My name is Yuju Lu. I'm working on front-end graphics for many years. So today I'm talking about texture. First, I will give a rough introduction about the history of texture, and we'll also talk about what's new with the texture. And there are also a few method options will affect how texture mapping works. And after that, I will give some demos and some applications with texture. Hopefully, this can give you some inspiration for some interesting projects. Texture is first introduced in version 8. And at the time, it only has one argument. And you can specify 1D, 2D, or 3D texture data. Like this, or you can also specify expression could be rasterized as a 2D image. But together with it, you need to specify vertex texture coordinates so that the parameter know how exactly the mapping works. And to make it work correctly, you have to make a vertex texture coordinates match the dimension of texture. When it was first introduced, only polygon and the field curve support this functionality. Here's an example of different dimensions of texture supported. And then there's a lot of plot functions so to provide a texture coordinate function and a texture coordinate scale. And this helps to generate vertex texture coordinates and in those plot functions, and makes text mapping widely used, and also gives a lot of nice applications. But however, still most of the visualization does not do this texture mapping functionality. The main reason is that most of the primitives does not support texture mapping. So recently we extended the texture object so that it could have a second argument. The second argument is text mapping option. It will pass down to each primitive, and without knowing the very explicit vertex texture coordinates, and it will tell the primitive how to generate these texture coordinates. And for 2D, potentially there could be for option values, and you can also tell the primitive to apply texture or not apply texture. The way it works is like other directive pushing down to primitives. However, primitive could choose to specify a local texture mapping to override it. Like here, this explicit screen planner overrides the value passing down. And user could also choose to specify an explicit vertex texture coordinates. It still works like before. And the primitive will consider vertex texture coordinates and the text mapping equivalent. So whoever comes first will get respected. Then how this planner and the screen planner works. And it will compute the local bounding box of the object for here, like a polygon field curve, disk rectangle, and also graphics complex and graphics group. And based on this 0, 1 range, it will do some linear interpolation together with the coordinates, and then generate the texture coordinates and push it to hardware together with the vertex coordinates. The difference between planner and screen planner is computed based on the user coordinates, and the screen planner is computed on the screen coordinate space. which means that planar will apply to object first, then we will apply the geometry transformation so that the textures stick to the object. But the planar is you transform the object first, then apply texture. It's always it's always the same orientation. This could be for different purpose of use. For example, like a text. Screen planar support text, so now you can apply different styles to text through texture, and you can, do a lot of fun things with that. Multi-primitive will work as a whole group. Like here, there are 2 disks specified with the same disk box. It is considered as the whole object. But the user, if you want to apply texture separately, you just need to have 2 separate disk boxes. It will just work that way. Same thing for polygon as well. This is a random sampling of image to generate some nice effects. By the difference of its nature, 3D graphics has different text mapping values. For example, like box, cuboid, cubic, cylindrical, planar, spherical. Here are a few illustrations shows how this mapping roughly works. For example, like a box and cubic, it will roughly assume the data, the polygons object is roughly close to a cuboid. Then the difference between box and cuboid, cubic is the box applies 6 directions, cubic apply 3 directions. So then the top and the bottom will be same textures, same orientations. And so with this new functionality, now all face-based primitives now support text mapping option. And if you specify a texture, it will be supported by default. So this is the 3D graphics example, works with texture. And what automatic means for these different primitives? It will mean different things for sphere, cylinder, cone, and the B-spline suffix just for the different geometry shape. But for the rest of the primitives, it will behave as a box, and unless it is specified explicitly. So here gives a list of geometry shapes and all the different mapping method, how does it works. And so you can go through them and pick the one close to what you want and select that one. For planar and the spherical in 3D, you can also specify directions. Like by default is Z direction, apply top down. But also you can customize it. Like here, it's bottom up instead of top down. It's negative Z, this is Z. Same thing for Y and negative Y, X and negative X. Cylindrical texture has some very unique computing based on box ratios and also the height of the cylinder, so that the map on the surface is always uniformly distributed. And the same thing for cone as well. Stereo graphics is a special text mapping method, and you could also specify direction, and together with it, you can specify scale. This is some example that show you how it works. You can specify scale. You can roughly know now how this mapping works. And you can also specify directions. And combined with there's method options I will describe after this. So it could generate different combinations. And B-spline surface should work with all the named texture mapping described above. And but beyond that, there's also 3 specific named texture mapping work with B-spline surface just because of the nature of how the B-spline surface works. User need to specify U and V direction control points. So it's it makes more sense to apply texture around both on the U and the V directions. And here are a few B-spline surface examples. And Mathematica, the default case is a unified wrap. And you can see this is UV wrap. It totally depends on the samples. And you can see if there's more samples, and there's more texture squashed together. And the unified one is even out, so that the uneven distribution could be ruled out. But however, because of this side is much shorter than this side, there's no ideal solution for that, and we have stretch so that this banded area looks more even. So these two will give different perceptions, like object. Like this is more feel like, and these are more like an object banded. But this is more like a hard carved object, like a wood and stone. So based on different needs of the user, you can choose the right mapping method. Here a list of more B-spline surfaces and how these 3 named texture mapping works. Most of the cases, they are looking pretty close in general. And here is a 2D B-spline surface example, and then we compare it with planar, and you will see that it works UV direction instead of XY direction. There's also a few method options will affect how texture mapping works. Texture wrap is one of them. For texture coordinates, we know that it will within the range of 0 and 1. What about those coordinates beyond that? How do we deal with that? Now, user can decide how to deal with that. By default, it's a repeat. And you can choose to clamp to edge, like the edge color extended for rest of the directions, and also mirror the repeat. Compare these two, and also just clamp to border, just clip it out. There's also texture sampling, and there are 3 options: nearest, linear, and anisotropic. And nearest will give sharp results. In some cases, you'll find it useful, but it will have aliens artifacts, especially when the texture is big. And linear, smooth out. The point, if there's more textures squashed into 1 pixel, it's too blur. And the default anisotropic has much less aliasing artifacts, and also for those more pixel area, it looks much better. Here is a combination of texture wrap and sampling, so it can give you a better idea with just a few pixels, how it works. And there's also min-map functionality. By default is on. It will use some of the memories to generate subsize textures, and during rendering, it will choose the right one based on how big is the object. And you can see this squashed area, it looks much better with mipmap on. User could choose to turn it off based on their needs. And then we also have cache or texture method. By default, we only caching one textures at a time. So if there are multiple textures, we'll switch between them, pushing to hardware. But if you turn it on, user could choose to caching all the textures. The good thing is about it will run once the application loaded, like a game engine, it runs much faster because everything is already on hardware. But the user need to be responsible for the GPU memory. So here is both of the images now. It's located in hardware. So now we'll show a few possible applications, and without knowing the vertex texture coordinates, and we will generate texture coordinates for you, and if you have a texture mapping method specified. But sometimes user might still want to control the scaling of the offsetting. And there's one possible solution is you can use graphics group, and it defines the boundary and changes this boundary and to achieve the offset and scaling. Another possible solution is to scale and offset the texture itself. Here is a 3D example. You can see, and you can also offset it. Here is a different example, and it just works. And texture is a way to feed data to GPU. And other than texture mapping, you can also do a lot of different things like normals. You can feed in the data as normals, and the material shading will provide computing, more sophisticated computing, and deal with these texture coordinates. So here, with this normal map, you can see so many details that you can have. Each of them have different depths. And here is a more complicated example. It has a list of the textures for different purpose, and the material shading will stack up all these 2D textures and get a 3D texture, push it to hardware, and hardware program will decide how to make use of them. And it will still work with texture mapping method. So this is a spherical default, and this is a planar texture apply top down, and this is cuboid. This is a box. So you can see that it gives totally it's different perception of how the object is, and how this material feels. In case of interested about the material shading, and if you dig deeper, you can see that it Ctrl Shift E, but see it is implemented with surface parents. The nice things with all these fillings and shadings is it's 100% transparent, the implementation, and you can print out all the implementation details by this building functions. And here is how this material shading works, and it's built on top of Material X, and which is a library from Google. And if you're interested, you can also make a copy of that, and trying to change something and build up your own material shading. Here is an example you can do with texture. You can map a video, dynamic video, to a 3D object, and you can see on the performance. It's really fast. You can even zoom in and rotate it, and makes your 3D application more fun. This year, I noticed that there are quite a few talks related to GPU. And for me, I think graphics is the closest to GPU hardware, and texture is a better way to feed data into GPU. And user can also have a way to how to make use of these texture data. And we have a few new features like image effects. It will use the off-screen rendering result as a texture internally, and then apply different effects on top of that. Same thing for image and raster box. So here you can apply 3 different levels of leaves, and with different blurring on results, and then generate something nice. And of course, you can apply to 3D through inset as well. So the 3D can also has those post-processing effects. So in case you are wondering how these things blurring works, you can also print it out, all the details. You can grab it and define your own surface appearance and try it out. Here is an example of video effects. And since the raster box internally is a texture pushed into hardware, you can also apply different effects on top of that at the time of rendering. Here is a list of effects predefined. It's built in, and you can apply to any videos you want to apply. And the computing it happens totally on GPU, and what you need to do is just pass down the computing algorithm, so that the hardware knows how to deal with them. Again, in case you're interested how this TV is implemented, it's quite simple, and you can grab it and play with it, change something, and build up your own image or video effects. And hopefully this can be useful to inspire you for some interesting projects. And okay, then I will go through some of the questions if there's any. If there's not, then we're done. Oh, one of the questions from Jim is like, would it possible to have a copy of notebook? Yes, or the notebook will upload it, and together with all the other top notebooks, you can download it. Patrick has a question: is there an ocean wave-like texture available? Is that an easier way to create one? Then, if you are quite familiar with some of the mathematics, you can generate one yourself. Otherwise, you can also try to Google it. There's always some open pictures available used for gaming reasons. And you can try it out, download and try it out. For built-in, we do not have ocean wave textures. And for the chat, yeah, there's a question about is that possible to import textures? Yes, you can always use the function of import, and then it will just work with a texture. Like here, you're using an import for videos as well. And yeah, that's all. Thank you for listening, and have a nice day. Bye-bye.